Okay, so this is going through the chemistry mock, the Combined Science High paper that you did in December. So we start with question 1. It's telling us straight away that the whole of this question is about the extraction of aluminium. So when you get any information that is before a part of a question, so this is 1.1 here, what I'm underlining, for example, then what this is saying is this is referring to or this could be relevant to any part of the remaining question, or the whole question, I should say. So they're beginning with us by telling that we've got an aluminium atom. So the first thing to sort of pay attention to when you're given that information is that if they say the word atom, they're talking about something that is neutral or neutrally charged. So what that also means is that protons equals electrons. Okay, that's implicit in the word atom. If it was a different number of protons and electrons, we'd be talking about an ion. So then they give us the symbol from the periodic table for aluminium with the two numbers that we see on the periodic table. So let's just go to the periodic table and have a look at that. If I zoom in there, you can see that's where it is. So they're presenting that information, and they ask for the number of electrons and the number of neutrons in the aluminium atom. So one of the things is that when you look at the periodic table and you look at the key, you can see that the bottom number is the atomic number or the proton number. And we have already said that because this is an atom, the protons equals the number of electrons. So if we know that this is the number of protons because it's the proton number 13, then we also know it's the number of electrons. So that's what we're going to write, 13. Then it asks us for the number of neutrons. Again, looking at the key, we can see that the top number is the mass number, right? And when we think about the relative masses of the different particles that make up an atom, a proton is 1, a neutron is 1, and then an electron is very small. So an electron does have mass, but it's very, very small. And so when we're looking at the mass numbers, it makes no difference. So what that tells us, or what we can sort of think about here, is that 27 is the number of protons plus neutrons. And we know that that equals 27. Now we have already said, we've already got the proton number, sorry, so we've already said how many protons we've got. So we have 13 protons plus however many neutrons it is we've got equals 27. And if we subtract 13 from both sides, we get 14. So our number of neutrons here is 14. Okay. Now they're telling us about the actual extraction of aluminium. And one of the things that they're making very clear is that it's by electrolysis. And this diagram here is a diagram of the type that we should recognize simply. Well, it is a type of diagram that you would only see in relation to the extraction of aluminium. So it's a mixture of aluminium oxide and cryolite. I don't think they ask us about cryolite in this question, but cryolite is a substance that aluminium oxide is dissolved in, and that lowers the melting point of the aluminium oxide, which saves money because we can do the extraction at a lower temperature. If we look at the diagram, they have labeled it for us, but actually one of the things they haven't done, which is going to be relevant to one of the questions, is they haven't said what the actual electrodes are made of. So we can see we've got the negative electrode, and we can see we've got the positive electrode, and on the diagram both electrodes are the sort of black parts of the diagram. So we've got, for example, one there, and we can see part of the negative electrode there. And what you have to remember when it comes to the extraction of aluminium is that those electrodes are made of carbon. This is going to be relevant. Okay, so that's also made of carbon. So both of them have made of carbon. Okay, so I'm just getting some of the information ready for perhaps a little in a moment or two. All right. Now, next question is aluminium is produced by reduction. And then they ask what is meant by the term reduction. Now, there are two meanings of reduction, or no, well, they're both correct. One is more useful than the other. So reduction can mean the loss of oxygen. Okay, or so if you think about oil rig, oxidation is loss and reduction is gain of electrons. So gain of electrons. Now in this, in the mark scheme, the main answer they give is the loss of oxygen, because we're going from aluminium oxide to aluminium. But it is still correct to say the gain of electrons. So you can absolutely do that. But in this, if we're talking about metal oxides producing the metal, and they're asking about reduction, if you can see there's a change in the oxygen is removed or gained by something, then you can refer to oxygen in terms of oxidation and reduction. So obviously oxidation is the gaining of oxygen and reduction is the loss of oxygen. But if you do talk about the loss or gain of electrons, that's still correct. So we'll just put the oil rig here just to remind ourselves. So that's oxidation is loss, and that's of electrons. And then reduction is gain. Okay. Right. So this is a bit where the carbon part of it is important. So you've got carbon electrodes and oxygen is being formed at these electrodes. Now, oxygen is an incredibly reactive element. So what's happening here is the oxygen. So this is 3 marks. So this is how we would think about the different marks. So oxygen, or the oxygen formed, but the oxygen reacts with carbon. So as the oxygen is being formed at those electrodes, it's reacting with the carbon. So that's 1 mark. Whoops, sorry. Reacts with carbon. Now, there's a consequence to that. If you're reacting carbon and oxygen, you're going to get a product, and that product is CO2. Now, if we were thinking about this in terms of state symbols, our carbon is a solid, our oxygen is a gas, and our CO2 is a gas. So we are, in effect, removing the carbon, or the carbon is being lost because, or it's not being lost, but it's being made into part of carbon dioxide. So what happens, or the way we refer to it, is that the electrode wears away or burns away. So the electrode wears away. So as more and more oxygen is formed, the carbon is reacting with the oxygen to form the carbon dioxide, which means that the electrodes themselves are shrinking because the electrode wears away. And what we haven't actually said in our answer yet, although I've thought about it in my thinking, is that the electrode wears away because it's producing carbon dioxide. So this is a particular feature of electrolysis where we're extracting aluminium. So there are electrolysis questions which can be about any aspect of electrolysis, as it were, or anything that involves electrolysis, but there is one part of the electrolysis part of the course which is specifically about the extraction of aluminium. It has some unique features, one of which is the fact that the electrodes have to be replaced every so often because the oxygen that's produced reacts with the carbon in the electrodes, forming carbon dioxide. Okay, and then we get to the final part, I think, of the question. And it says, a substance conducts electricity because of free-moving charged particles. What are the free-moving charged particles in A? And then we've got different types of substances. Now, in chemistry, and actually it's not just chemistry, I think, but anyway, we're just focusing on chemistry here. can only be, these free moving charged particles can only be ions, and of course they've got to be free to move, or electrons, specifically delocalized electrons. So these are the only things in chemistry that are mobile charges, right? So whenever you're thinking about something conducting electricity or not in a chemistry question, you're going to refer to one or the other, really. So if we think about the carbon electrode, they told us that it's made from graphite. And one of the features of graphite is that each carbon atom only has 3 bonds. So that means only 4 of its outer electrons are used in bonding, which means there is a spare electron. There's a spare electron from every carbon atom. This spare electron becomes delocalized or is delocalized. So that means every carbon atom is providing a delocalized electron. So there's loads and loads of delocalized electrons, and it's those that are then free to move through the structure and carry charge. So our answer here is delocalized electrons. The molten mixture of aluminium oxide. Now, aluminium oxide, so we've got a metal and a non-metal. Aluminium is a metal, oxygen is a non-metal. So this is an ionic compound. And it's molten, which means the ions are free to move. So what's going to carry the charge here are going to be ions, the Al3 plus ions and the O2 minus ions. And then finally we come to the metal wire, and metals, they are, if we think about the metallic bonding, that's a strong electrostatic attraction between positively charged metal ions and delocalized electrons. So again, we have got delocalized electrons. So if we're talking about electricity being conducted, and we're talking in a chemistry question, it has to be mobile charges, because remember, current is the flow of charge. So something has to, a charge has to be able to move. It can only be ions or delocalized electrons. All right, so this question here takes us right back to the beginning of year 10, right to the very start, really. So they've told us that cesium is in group 1 of the periodic table. And we could see that if we looked on our periodic table. And it asks us to explain what happens to cesium atoms when cesium reacts with oxygen to produce cesium oxide. Now, one thing that can help you, although, you know, this is something to try and get your head around. Well, actually, sorry. So we've got group 1. So it's going to group 1 form 1 plus ions, right? This is how our periodic table can help us. And it's reacting with oxygen, which is group 6, and they form 2 minus ions. Now, when you're answering questions in chemistry and they give you a specific element or a specific substance, you really want to be answering specifically about them. So it's 4 marks. When cesium reacts with oxygen, each cesium atom loses 1 electron. Okay, it's in group 1, has 1 electron on the outer shell. All bonding, the consequence of all bonding is a full outer shell. If it's in group 1, it's got 1 electron in its outer shell. It's going to lose that 1 electron to achieve a full outer shell. So it loses 1 electron. So you've got to be specific. Don't just say it loses electrons or loses. Please be very specific about the number. So each cesium atom loses 1 electron, and each oxygen atom. Now, oxygen is in group 6, which means it's got 6 electrons on its outer shell. The reason it forms 2 minus ions is because it needs to gain 2 electrons. So each oxygen atom gains 2 electrons. Then we could say to form. So what is actually formed here? We form cesium ions, cesium plus ions, sorry, and O2 minus ions. Okay, so we've said that cesium loses 1 electron each cesium atom. We've said that each oxygen atom gains 2 electrons. We've said what the result of that is. We form a cesium plus ions and we form O2 minus ions. And of course, what we're ultimately making is cesium oxide. So really, we should make it clear. You know, one thing we can do is to give the formula of the compound. So we can say resulting in, and this is where you have to use your you have to think about how to work out formulae. So we've got cesium plus, oxide 2 minus. This is just a reminder of a little rule that we did. Whatever the number before the charge is goes after the other ion. If they're both the same number, it's just one of each. So what we've got here is cesium 2O. So that can be our final answer. Other possibilities is that we could have said for every cesium atom, or for every cesium atom that loses 1 electron, for every 2 cesium atoms, that lose 1 electron, an oxygen atom gains 2 electrons. But I think actually this is probably, for the purpose of our answer here, easier. So that is 4 marks. 1 mark, 2 marks, 3 marks, 4 marks. This also takes us back to, in fact, this possibly even takes us back to year 9, although we would have touched on it again, or we did talk about it again in year 10, start of year 10. We've got to explain why cesium is more reactive than sodium. So let's just see where they are on the periodic table, because we're making a comparison between 2 elements. So there's cesium and there's sodium. So they are both in group 1. If they're both in the same group, that means they have similar chemical properties. So they've both got 1 electron on the outer shell. They're both going to lose that 1 electron when they react with a non-metal. They're both going to form ionic compounds, and so on and so on. So what is it about it that makes the reactivity? And in a sense, the way to think about that is how fast or how quickly reactions take place as a way of thinking about reactivity. How can we explain there being a difference in how fast those reactions involving those 2 elements happen? And they're telling us that cesium is more reactive, right? So they're telling us that the one further down the group is more reactive than the one further up. Now, when they react, they are losing an electron. So whatever the reason is, has to be about losing the electron. And that's why it's given us a bit of a clue by saying in terms of electrons. So we can phrase this in different ways. So let's just think about how we would represent those atoms in the first place. And you've done lots of things to do with energy levels and shells. So we'll start with cesium has more energy levels. Okay. What does that mean? It means, so therefore, the outer electron, the one that's going to be lost, is further from the nucleus. Okay, so what's the consequence of that? So we've got more shells, which means the outer electron is further away from the nucleus, which means there is a weaker attraction. So resulting in a weaker attraction. What's the attraction between? Well, between the nucleus, which is positively charged, and the outer electron, which is negatively charged. And so if we have a weaker attraction, what does that mean? It means the outer electron is lost more easily, or is more easily lost. So cesium has more energy levels, therefore the outer electron is further from the nucleus, resulting in a weaker attraction between the nucleus and outer electron. So the outer electron is lost more easily. Okay. 4 marks, right? It's a sort of a classic question. It's one you can absolutely get your heads around. But 4 marks, 1 mark, 2 marks, 3 marks, 4 marks. Okay. So we're now on a question about gold. It's asking us why is gold found in the earth as the metal itself? So what that means is, why is it found as an element, as made of only one type of atom? Why is it not found in compounds? And that is all to do with reactivity. So the reason it's found as the metal itself is because it's unreactive. Why do atoms of gold have no overall electrical charge? So we've touched on that in the very first question when we were trying to work out the number of neutrons and electrons in aluminium. Because they have, I would use equal instead of same, right? So they have an equal number of protons and electrons, and that is fundamental to the word atom. They use the word atom, they are telling you that you have an equal number of protons and electrons. Okay, so this was a question that wasn't answered very well, and it was asking why gold is easily hammered into shape. So why are metals? I mean, this is about gold, but gold is an example of a metal. This is what will happen is we do in class, we do types of substances like metals or ionic compounds, but then in an exam question they'll pick a particular metal or a particular ionic compound, but everything we've spoken about referring to those types of substances will apply to that specific example. So essentially it's asking us why is it that metals are malleable? And one of the things you'll notice about this diagram is if I just do this, hopefully you can see that what we've got is a series of layers. And that word layers is very important, especially for our answer. And those layers just sit nicely on top of each other. If I was to apply a force at one end to one of the layers, that layer would be able to slide across. And that is the key to this answer. So it's 2 marks. First mark is really saying that it's layers of atoms. So it's really that word layers. And then the second mark is simply can slide over each other. Okay. Right. So a necklace contains 9.85 grams of gold. 1 mole of gold contains 6.02 times 10 to the 23 atoms. Calculate the number of gold atoms in the necklace. Give your answer in standard form. So they are saying that, or they're telling us that 1 mole equals 6.02 times 10 to the 23 atoms. Okay, they have given us a mass, right? Given us the mass of gold, and they have given us, well, they've given us an AR, but it's an MR, right? So in terms of thinking about formulas, you might want to. It is AR because it's an relative atomic mass, not a relative molecular mass. But in terms of our calculations, if we know a mass and an AR, we can work out moles. So number of moles equals the mass we have divided by the relative atomic mass or the relative formula mass, whatever the mass of the formula is, and it's just AU. So 197. That gives us an answer of 0.05 moles. So 1 mole equals 6.02 times 10 to the 23 atoms. Therefore, 0.05 moles, so a fraction of 1 mole, equals 0.05 times 6.02 times 10 to the 23, which equals 3.01 times 10 to the 22. So that's what they were wanting us to do here. So we would have got 1 mark from doing this calculation, 1 mark from knowing this is what we then had to do, or actually this calculation, and then 1 mark in the end. They've asked us to give the answer in standard form, so we have to make sure that we give the answer in standard form. So that's where the marks come from. We have got 1 mark, 2 marks, 3 marks. Another electrolysis question. All right, so a teacher demonstrated the electrolysis of lead bromide. This figure shows us the apparatus used, so we can see there's a circuit. It's an ionic compound, they tell us. Now we're into the first part of the question. It's a giant ionic lattice when it's a solid. So now, the first question, don't be thrown by the fact that we've got this electrolysis information. So that all this is could apply to any part of question 4. When we get to 4.1, it's asking us simply to describe the forces of attraction in solid sodium bromide, lead bromide, sorry. I'm sorry about that. So we need to be able to do that. And really, this is one of those sort of stock phrases. So in an ionic compound, well, basically we're describing the ionic bonding, okay? There are strong electrostatic, you must use that word, forces of attraction. See, they've already used the phrase forces of attraction. So you have to sort of build on that and make it clear that they are electrostatic forces of attraction. Now, whenever you're doing any forces of attraction, what are those attractive forces between? Well, in an ionic compound, they are between oppositely charged ions. Okay, so there's our second mark. And of course, they've told us in a lattice, and we've got to just think about how our phrase carries on. But our phrase is in all directions. Right? Up, down, left, right, etc., etc. Right? In all directions. We'll just put in the lattice to make it clear. But that is 3 marks. Must use the word electrostatic because they've already used forces of attraction. So electrostatic forces of attraction between oppositely charged ions in all directions. Okay, so then there's a definition, and these are easy marks to sort of forget, but also easy marks to learn. But asking what an electrolyte is isn't a very common question. But anyway, if the best definition for this is a substance. There's not really much of an explanation here. A substance broken down by electricity or by electrolysis. Okay. think that's just one of those phrases, one of those definitions. Explain why electrolysis takes place only when the lead bromide is heated. Well, the beginning of the very first part of this question has been explain about the forces of attraction in the solid ionic lattice. So the thing is, in a solid particle diagram, even going back to year 7, the particles vibrate about a fixed point, so they can't move. Right, the ions are not free to move. You need to produce a liquid for that to be possible. Still how you would have thought about a year 7 particle model. So explain why when it's heated. So you've got to make it clear. So they're saying heated. You've got to make it clear that it melts. All right. So lead bromide is melted so that, so it's 2 marks, so that the ions are free to move. Okay. And then we get, this is a hard question, all right? So it's a half equation to show what happens to the lead ions during the electrolysis of lead bromide. Now, giving us a formula, when they give you something, it's a clue, right? Or it's something to help. Now, if we look at that formula, we can see that we have 2 times Br. And the thing is that we're talking about an ionic compound. If we look on our periodic table, find where Br is. If we're thinking about what ions that would form, well, it goes -1, -2, -3. Okay, so this is going to be a -1 charge ion when it's an ionic compound. So I'm going to put that minus there. So there are 2 1- charges. Now we know that in a formula, it shows the ratio of, if it's an ionic compound, it's showing the ratio of ions, and it's showing the ratio so that the overall charge they cancel out, sorry, so the overall charge is 0. So if we've got a total charge from 2 bromide ions of -2, and we know that overall the overall charge in the compound is 0, then that tells us that lead must be 2+. All right, that is how these numbers cancel out to form our overall uncharged compound. Now, a half equation is always about whether electrons are lost or gained. A half equation is showing us either oxidation or reduction. So we are starting with lead ions. Okay, and we know in reduction, we know, or one thing to remember, from in electrolysis is that you always get the elements at the end. All right, so if we've got the lead ion at the beginning, we must have just lead at the end, right? In electrolysis, you're always forming the elements, right? They're always the product. So we've got to get from 2+ to 0, and the way we would do that is gain 2 electrons. So it's 2 marks. One of the marks, or the first mark, is for recognizing you go from 2+ of lead, 2+ to lead. And then the second mark is by making sure you have the right number of electrons on the correct side of the equation. Okay. Right, so we're now on to the next question. So iron is found in the earth as iron oxide. And then it asks us to define the term compound. So we've got to explain what a compound is. So again, this is actually even an answer that you might have learned or should have learned. I don't know whether it would have been year 7 or year 8, but it would have been one of those 2 years, and then it's come up again and again. So a compound is a substance in which atoms of 2 or more elements, or you can say more than one element, right? But 2 or more elements are, and this is a crucial bit, are chemically combined or chemically joined or chemically bonded, right? Any of those terms there. Okay. So now it says the equation for the extraction of iron from iron oxide is, and then they tell us it's iron oxide plus carbon monoxide produces produces iron and carbon dioxide. It says name the reactant which is oxidized. So we're looking, it's one of these two things because it says name the reactant. So why don't I highlight that? So if it's a reactant, it's got to be one of those two on the left-hand side because it goes reactants on left, products on the right. So it's got to be either iron oxide or carbon monoxide. And if we remember to what we talked about or what I mentioned earlier on the video, one way to think of oxidation or being oxidized is gain oxygen. So when we go from here to the other side, are we gaining oxygen? No. If we go from here, are we gaining oxygen? Yes. So it is carbon monoxide, and our reason is how we would have worked it out. It gains oxygen. Okay. Now we've got a mass calculation. So calculate the maximum mass of iron from 500 tons of iron oxide. Now we look at the tons and we can be thinking, oh my gosh, I've got a big unit conversion here. However, our final answer is also in tons. So we can get away with not having to convert the units because our starting units and our final units are the same. They've given us the relative atomic masses. They've given us the formula. So the first mark is to do the MR. So the MR of iron oxide, of the iron oxide that they've given us, well, we've got 2 ions. Sorry, mispronouncing that. I'm sorry. 2 iron atoms in the formula. So 2 times 56. And then we've got 3 oxygens. And so we add all of that up together and we get 160. Now, it's asking us for the maximum mass of iron that we can get from this. So if we had this amount of iron oxide, the amount of iron we could get would be the amount of iron that's in that iron oxide, which is this. So there is a percentage of our iron oxide is iron, right? So that would be, so what's that? That's 112. So if I had 160 grams of iron oxide, I would have in it 112 grams of iron. So it's a fraction, and that's how we now work the answer out. We take that fraction, so we take the amount of iron that's in our iron oxide as a proportion, as a fraction. Okay, so it's 2 times 56 over the 160. We multiply it by how much iron oxide we've got, and we get what our maximum yield could be of iron. So it would be 350 tons. If that's not clear, or if you're unsure about that, then just let me know and I'll try and make it clear. I'll try and go through it with you. Okay. All right. So now we've got a student did an experiment to produce iron chloride solution. This is a summary of the method the student used. So they've got, they add iron to dilute acid. So what we got? We've got a metal. We've got an acid. We are making a salt. Okay. Now, we've got MAS. I'm hoping this will prompt you to think of mnemonic MASH. Metal plus acid produces a salt plus hydrogen. And this is our colorless gas here. So our colorless gas is hydrogen. So write a word equation for the reaction. Now, when you're writing word equations and they've told you what the substances are, or they've told you what some of the substances are, and you can deduce what any remaining ones are, you must absolutely say, okay? Now, if you're making a chloride, then the acid you're going to use is going to be hydrochloric acid. That's one of the things that this question is testing. It's testing two things. It's testing that you can recognize what the acid would be, and it's testing your ability to recognize what the gas would be. So we are adding iron to hydrochloric acid. We are making iron chloride. And then our colorless gas, which is hydrogen. Okay. So then they tell us that the iron chloride solution collected in the test tube was not pure because it contained some acid. So what that means is that we haven't added enough iron because not all of the acid has reacted. Okay, that's really the crucial thing there. So what it's saying is the acid is in excess. And then it's asking then, it's not pure, it contains some acid. Describe detailed instructions for step 1 to make sure the iron chloride solution collected in step 3 is pure. So we want to make sure that we want to react all of that acid. Now, if you remember when we did the making a soluble salt, we added it wasn't a metal, it was a metal oxide, but we added it to the acid so that it was in excess, so that the metal oxide was in excess. How did we know it was in excess? How did we know that all of the acid must have reacted? Because there was no longer any reaction, and so we got as we added it, it disappeared because the reaction took place, and then once it no longer disappeared, it meant we'd added it in excess, right? But the other thing that we did was we heated the reaction mixture. So what we're going to do is we're going to heat and stir the mixture. Okay, and then we're going to add excess, all right, iron. And then how do we know if the reaction is complete? Add excess iron until no more gas is produced, because that's another observation we can make. Gas is produced. And then we're now going to have iron in our mixture. So we're going to filter. Yeah, and that's it really, right? Filter the mixture. So, I think it's a little bit tricky for 3 marks, I'll be honest, but I'm hoping 1 or 2 marks should be okay, right? Should be relatively straightforward. But if you have any questions about that, please let me know. Okay. Okay, so question 6. This question, on the whole, was well answered. But we're still going to look at it because we can learn some useful things beyond just simply this question. So whenever you get a table of results, one thing to bear in mind is that the left-hand side, or the left-hand column, is the independent variable. And if we were plotting this on a graph, that would be on the x-axis. And the right-hand column is the dependent variable. And if we were plotting that on a graph, that would be the y-axis. So it asks us, this first question asks us, how does increasing the volume of hydrogen chloride affect the pH? So this is the increase of hydrogen chloride. What is happening to the pH? Well, that's decreasing. So we've got it's best to talk about what it is that you're actually measuring. So what we should say is, to get the best answer is, as the volume of gas increases. Okay, so as this volume here, as this volume here increases, the pH decreases. Now you could have said it becomes more acidic, but we may as well use the terms, the labels that are in the actual columns. This one, again, a lot of people were able to get the 1 mark. Where they maybe didn't get the 2nd mark is that they weren't specific enough. So if it's saying doubling the volume, right? So the question says, describe how doubling the volume of water affects the pH of the acid. So that's times 2. That's times 2. So this is the doubling. That's times 2, right? So that's the doubling. Now that's it's a very clear change that they're making. So we want to see, is there a very clear change in the pH? Well, the change there is plus 0.3. Change there is plus 0.3, and the change there is plus 0.3. So whereas before we just had to say, as this increased, that decreased, but it was only 1 mark. This is 2 marks. As this doubles, if you simply say the pH increases, you will only get 1 mark, I'm afraid. So what you need to make clear is actually what exactly is the relationship. So as you double the volume of water, the pH increases by 0.3. Oh, sorry, as the volume of water doubles, sorry, I'm not being very clear there. Sorry about that. So as the volume of water doubles, the pH increases by 0.3. Okay. All right, which ion makes a solution of hydrogen chloride acidic? I really, really, really hope this isn't a sort of question you get wrong, right? So we know that knowing whether something is acidic or alkaline is all about pH. And that H is H plus ions. All right, so every acid has hydrogen in it. Hydrochloric acid, HCl. Sulfuric acid, H2SO4. Nitric acid, HNO3. Phosphoric acid, H3PO4, right? It's the hydrogen ions, the hydrogen positive hydrogen ions. Give an indicator to show that hydrogen chloride solution is acidic. So we only use one indicator in in our GCSE, and that is called a universal indicator. And we have to say what color it would be in an acidic solution. Now the way that indicator works is it actually follows the colours of the rainbow. Red, orange, yellow, can't really see that, but anyway, green, blue, and then purple. Okay, and well, you know that, or you should do, that green is the colour when it's neutral. And so to say what colour it would be in an acidic solution, we can say any of the ones to the left. So we can say red, orange, or yellow. So I'm going to say red. All right. Now it's got a question which is about concentration. So it says 0.152 grams of hydrogen chloride is dissolved in water to make 250 centimeters cubed of solution. Calculate the concentration of the solution. Give your answer in grams per decimeter cubed. So grams, we've got that at the beginning and we've got that at the end. Great. So no conversion to be done there. However, we've got centimeters cubed at the beginning and we have got decimeters cubed at the end. So we are going to have to make a conversion. We are going to have to turn centimeters cubed into decimeters cubed. All right. So there are 100 centimeters in a meter, and there are, because it's a centimeter, sorry, 100 centimeters in a meter, yeah. And then there are 10 decimeters in a meter. So a decimeter is 10 centimeters. And a decimeter cubed. So just trying to help you remember, you could just learn what the conversion factor is, but let's just give you a sense of it. So 1 decimeter equals 10 centimeters. So 1 decimeter cubed must equal 10 centimeters times 10 centimeters times 10 centimeters, which equals 1,000 centimeters cubed. So we do not have 1,000 centimeters cubed. We only have 250. So we have a fraction of a decimeter. Volume. Oh my goodness, sorry. Volume equals our 250 centimeters cubed divided by 1,000, because that's how many there are in a decimeter cubed, equals 0.25 decimeters cubed. So you needed to make that conversion. So now we're being asked to work out the concentration, and you know, you could be sat there going, oh no, what is the equation for that? What's the formula for that? They've given it to you. When you look at that, that is grams divided by decimeters cubed. And we know that the grams is 0.152. And we know the decimeters cubed is 0.25 because we've just done that conversion. And so our final answer is 0.608 grams per decimeter cubed. Just to show you, that's grams and that was decimeter cubed, which is why that is grams slash decimeter cubed, grams slash decimeter cubed. Okay, so this is a longer question. In fact, actually, it's surprising it's only 4 marks, given the fact that we have to explain an experiment, and we're going to have to, when it says give valid results, basically what it means is that your experiment, your plan will work. That's all it means, right? So we're given 3 metals, X, Y, and Z. We've got to identify them. We're told that one of them is magnesium. We're told that one of them is iron, and we're told that one of them is copper. And it says to ask us to plan an investigation to identify the 3 of them by comparing their reactions with dilute hydrochloric acid. So that is a MASH reaction, right? So metal plus acid produces a salt plus hydrogen. Now, there are different ways we can do this. We could compare, we know that hydrogen's being formed, so we could compare the rate at which the hydrogen is formed. So basically how effervescent or or how many bubbles there are, per unit time. What we've got to understand, whatever method we use, is we've got to understand the difference in reactivity. So if you don't know which is the more reactive and which is the less reactive, you can only get so far with this question. So magnesium is the most reactive. Iron is next, and then copper. So there is that's a certain test of this to an extent. So anyway, we could compare the rate of bubbling, or we could compare the temperature change. So the more reactive the metal, the bigger the temperature change. So what I'm going to do is I'm going to write my method based on temperature change, just because I think that's the slightly harder one, or the one that maybe that isn't so obvious or clear to you. So we have to, if we're measuring a temperature change, what you've got to remember is that we're measuring the temperature before and the temperature after. So, and I think when you're giving a practical, it's best, or it's a good idea to put them in steps. So you can just treat it as a bullet point, or you can put one or something like that, the first step. So add a specific volume. I mean, you could say what it is, but a specific volume of a known concentration of hydrochloric acid to a test tube. To a test tube, and record its temperature. Okay. Number 2. Add a specific. We'll go for number of moles, because I actually think that's better. But if you wrote mass, it would be okay. So a specific number of moles of metal X to the acid, and record the maximum temperature reached. Yeah. So the reaction takes place, and you're recording the maximum temperature reached. Then we're going to repeat steps 1 and 2 with metals Y and Z using the same volumes, the same volume, concentration. So volumes, concentrations, and mass and number of moles, sorry. This is our control variables. All right, our control variables are we're using the same concentration of acid, the same volume of acid, and the same number of moles of the metal. Finally, so it's not a method as such. The greatest temperature change equals equals magnesium, apologies. And the smallest equals copper. And that will definitely get you all the marks. Okay, so things to watch out for is think actually what it is you're measuring, and what you're changing is the metal. So then how are you measuring? What's your dependent variable? So you could have picked the number of bubbles, or the rate of bubbles, or how much it's bubbling. The rate of bubbling, actually, sorry. I've gone for temperature change, so that's my dependent variable. So I'm changing, my independent variable is the metal. My dependent variable is in this, the temperature change. So I've got to keep everything else the same. So when you're describing how you're doing the first practical, make sure that when you do the you're doing it with the other metals, you're making sure that you've kept everything the same. Okay. All right, so metal M has two isotopes. Table 2 shows the mass numbers and percentage abundances of the isotopes. Calculate the relative atomic mass of metal M. Give your answer to 1 decimal place. So this relative atomic mass means average. So one thing to say is when you do this calculation, you've got an isotope with a mass of 203 and an isotope with a mass of 205. You've got different abundances, but the thing to hold on to when you do this calculation is whatever your answer is, it must be between 203 and 205. If you get an answer that is not between those two numbers, you have definitely made a mistake. If you're doing an average, your average must be between the two ends of your range. So the way you go about it, they've given it as a percentage. We know that 30% of M is always 203. And we know that 70% of M is always 205. So one of the things is that our final answer must be closer to 205 than it is to 203. So that's another thing we can take. If we're doing an average, though, we've got to divide it by the total percentage, which is 100. And we put those numbers into our calculator. Oh, it's 2 marks here. And we get our answer of 204.4. So our answer is within the range of our highest and lowest. But not only that, because we know that the greater abundance is with 205, it is closer to 205 than it is to 203, which also makes sense. It says to 1 decimal place. I've got my 1 decimal place. All right, table 2 shows the first 6 elements in the third row of the periodic table. So it's given us that. These elements react with halogens to produce halides. Aluminium reacts with fluorine to produce aluminium fluoride. Write the formula of aluminium fluoride. So this is about using your periodic table. So there is aluminium. It's in group 3. We're reacting a metal with a non-metal, so we're going to get ions. It's going to be a +3 ion. When we look at fluorine, it's in group 7. When that is in an ionic compound, that is going to form a -1 ion. Okay, so you do need to learn how to use your periodic table to be able to see things like what charges ions would be. So we go back. So I can say, well, look, I know that's going to be Al3+. And I know that this is going to be F- when they're ions. So if I do what I did before, earlier on, I showed you earlier on in the video, this is like your little shortcut. You look at the number, you put it after the other ion, providing they're different. If they're the same, you just put one of each. Okay, so we are going to get Al, and then there's no number after it. And then F3. So we're only focusing on the number of the charge, the value of the charge, sorry. And if it's 1, we're not putting anything. Okay. A molecule of phosphorus bromide contains 1 atom of phosphorus. The relative formula mass of the compound equals 431. So calculate the formula of this compound. So what we know is phosphorus, there's only 1 atom. We know it's got bromine, but we don't know how many atoms. So we're going to put X, and we know that that equals 431. So if I now subtract phosphorus from both sides, I get Brx equals 431 minus the value for phosphorus, which is -31. So that equals 400. And if I want to know how many bromines there are, I'm going to have X equals 400 divided by the mass of bromine, which is 80, and that gives me a value of 5. So that means I have 5 bromines. So it's going to be phosphorus Br5, and you could double check that by working out the MR. So it would be 31 plus 5 times 80, and it would give us 431. Okay, sulfur reacts with chlorine to produce sulfur dichloride, so SCl2. Complete figure 5 to show the arrangement of outer shell electrons in a molecule of sulfur dichloride. One of the things is, wherever there's an overlap, you are going to have to draw a pair or more than one pair of electrons. And when we show pairs of electrons, they are dot cross, right, or cross dot, whatever. Now this is where our periodic table comes in handy. So, number of covalent bonds. So it's only going to be about non-metals. And basically, again, we work backwards like we did with ions. So group 7 is going to have 1 covalent bond, group 6, 2, group 5, 3, group 4, 4. So 1 covalent bond, 2, 3, 4. Now, if we go back, chlorine is in group 7, so it forms 1 covalent bond. This is the overlap. That means we must write a dot and a cross, and only one, right? One pair of electrons, 1 covalent bond. Covalent bond is a pair of electrons, and we can do the same on the other side. Now, if I take the crosses to be the electrons of chlorine, and I look on my periodic table, chlorine is in group 7. So that means it has 7 electrons on its outer shell. So what that means is I must have 7 crosses if I've decided crosses are the electrons of chlorine. I've drawn 1, so I have to draw 6 more, and they must be with chlorine. So I can do that for both of them. Okay, and I can now just double check. So I've got 7 crosses because 7 electrons for chlorine. But also, how many have I got in total around the chlorine? I've got 1, 2, 3, 4, 5, 6, 7, 8. I have a full outer shell. Obviously, this is exactly the same. So now I look at sulfur. So my sulfur electrons are the dots. I've currently drawn 2. When I look at sulfur on the periodic table, it's in group 6, so it should have 6 dots on its outer shell. I've drawn 2, so I need to draw 4 more. Okay, so I have got 1, 2, 3, 4, 5, 6 sulfur electrons. And when I look at, now that it's covalently bonded, how many have I got in total? I've got 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 electrons, so I have my full outer shell. Okay, so now we're at the final question. It's telling us that hydrogen is produced on a large scale by reacting methane with steam. They give us the equation for this reaction, and then they tell us the conditions. And then we get to the first question, or the first part of this question. So it tells us that the reaction between methane and steam is an endothermic reaction. Now, if they're telling us that, that's important. That means energy is taken in. Okay, so endothermic reactions, energy is taken in from the surroundings. Then they ask us to complete the energy level diagram for the reaction on figure 6, and then they tell us what we should label, the activation energy, the overall energy change, and we should include the formulae of the products on the diagram. And the overall number of marks is 4. And the way the marks are going to be allocated is, firstly, that we show, the first mark is that we show that this is an endothermic reaction, so you have to remember how that is clear from an energy level diagram. The second mark is going to be from correctly labeling the activation energy. A third mark is going to be from correctly labeling the overall energy change. And then the fourth mark is going to be including the formulae of the products. So I'm actually going to start with the first mark and then the fourth mark. So in an endothermic reaction, energy is taken in from the surroundings, which means the energy stored in the products is greater than the energy in the reactants. So my line, or where my products are going to sit, is got to be higher than where my reactants started. So that's one mark. Including the formulae of the products on the diagram is going to be another mark, and that there is no excuse for not getting that because they give you the formulae. Okay, so we're just going to write those in. So 3H2 plus carbon monoxide, CO. So that is already 2 marks. Now in all of the energy profile diagrams that you do, you have that sort of, the hill. Okay. Now it's important to draw that, even though it's not been mentioned, because otherwise you can't show or you can't label the activation energy. Now I was really quite generous when I was marking this because I gave a lot of you the benefit of the doubt when it came to your arrows, because you basically put them in the right place, but you've got to be, a lot of your arrows were quite sloppy. You just sort of drew it freehand, and you've got to be so careful. Now you've got to make it absolutely crystal clear where your arrow begins and where your arrow ends. And from now on, if it's not clearly starting in the right place and finishing in the right place, then you will not get the mark. So it's got to start at the same height as the reactants, and it's got to finish, and I'm going to have to move mine slightly, it's got to finish at the highest point of the hill. Okay, so that is the activation energy. Now, some of you were drawing things. Hold on a second, let me just move where I'm writing that, sorry. So that's the activation energy. Now, some of you were drawing things like this. And that isn't clear enough, or like that. It's not clear enough. It's got to start at the right height and it's got to finish at the right height. I cannot stress that enough. It's exactly the same with the energy change. Here it's the difference between the beginning and the end. Okay, so you've got to make sure you start in the right place. Your arrow starts in the right place and finishes at the right place. So your arrow has to start wherever you're at the same height as your reactants and must finish at the same height as your products. And that is 4 marks. And in many respects, that's an easy 4 marks. Okay. What is meant by activation energy? So a lot of you wrote the amount of energy needed for a reaction to take place. And if you write that, you won't get the mark because you were missing a key term. The activation energy is the minimum energy, because you can have more than the activation energy. The minimum energy required for a reaction to take place. Minimum energy required for a reaction to take place. Okay, and then how does a nickel catalyst lower the activation energy? What you have to make clear is that it provides a different reaction pathway. So I'm afraid it's one of those things, it's like a definition, I guess. You've just got to learn it. So a catalyst provides a different reaction pathway. Okay. So, in a sense, both of these questions were definitions. But the key thing, a lot of you basically understood 9.2, but you didn't get the mark because that minimum is very important. And now, lastly, we had a bond energy calculation. In fact, it was only part of a bond energy calculation. You all did pretty well here, actually. So it says calculate the total energy needed to break all the bonds in 1 mole of methane and 1 mole of steam. And so you were going to have to break these bonds. So you can see that it was 4 carbon-hydrogen bonds and 2 OH bonds. So you had to add up how much energy was needed to break 4 carbon-hydrogen bonds and 2 oxygen-hydrogen bonds. So we've got 4 times CH plus 2 times OH. Put the numbers in. 4 times 435 plus 2 times 464. And we get our answer to that, which is 2,668, which lots of you did well on, so fantastic for that. And that concludes the run through of the paper. So if you have any queries, please let me know. Please contact me and I'll try and sort them out. But I very much hope that run through there was helpful.